stream is started. All right, Joel, take us away for tensor subclass serialization.
Sure. I'm going to share. Okay. Background here is this past week, Brian received an issue from Matthias Fay in Slack saying that tensor subclass D types are not being preserved through data loaded with multiprocessing. We track this down to some long-standing bug in the serialization logic, where D type was not being passed through to make wrapper subclass. It slipped through the testing. In putting in this fix, I realized that some other things are not preserved as well through serialization, and this affects both multiprocessing and torch save, torch load serialization. In particular, any of these like later on added dispatch on size strides policy, device layout types things are not preserved. So if you, for example, save a tensor subclass and then reload it, this stuff will not be correct and you'll get weird behavior. So this isn't good. We need to fix this. But it does require, as Alvin pointed out, kind of like BC breaking, I think, changes to this serialization format. Yeah, that's the background here.
Uh, Albin, do you want to talk more about the BC breakingness?
Yes, the short version, it's not completely BC breaking. It's more like we need to be very careful on how we do it to not make it BC breaking. The way serialization works is these rebuild functions need to stay there so that when someone loads an older checkpoint, they still have access to the old version of the rebuild function. So the old checkpoint should still behave the same as it always has. And we need a rebuild wrapper subclass v2, basically.
Fair enough.
So doable, we just need to be careful about it. I think the bigger question, I think, as Joel was mentioning, is like all these extra arguments that are more esoteric. And, we are adding more and more to these. What do people that add these think about it?
Okay, so before we talk about the arguments to make wrapper subclass, Albin, could you describe to us how plain tensor serialization decides what gets serialized and what doesn't? Because I also know for regular serialization, we don't actually faithfully record everything. Or I can try to explain it.
I think it looks very much the same, basically. We extract all the metadata by hand and stash that, and then we rebuild a tensor based
right,
on
but
that.
how did we decide what to stash and what not to stash?
I am not aware of any grand scheme or grand policy about it.
So
it's rebuild tensor v3, I think, at this point.
Joe, do you know how to get us there? Yeah, it's one of these.
Yeah, I think that's it. It also
so
sorry, go ahead.
Yeah, I think v3 is for some D types. v2 is used by some of the D types. v3 is used by the other set of D types. So just above is v2 in the same file. Yeah.
Mm-hmm. And at some point there is logic added to like traverse the dictionary or the state extra attributes stored on these tensors. Is that right?
Correct. So this is only to rebuild the C++ tensor object. All the extra attributes, dynamic thing coming from Python is added on top of that later on, yes. So here we basically said storage, offset, size, stride, recurse grad is what gets serialized. Everything else is dropped.
Okay, can we return to the wrapper subclass constructor? Okay, so essentially the concrete proposal is we're going to make a new rebuild function, which takes a bunch more arguments, but then there were too many arguments to rebuild wrapper subclass, and y'all don't know which ones we should actually save. Is that right?
Right, the same way we don't actually save things like layout, as far as I know, for regular tensors, or
Well, we
memory format.
indirectly save layout, right? Because if you serialize a sparse tensor, right, something special happens.
It,
Right. So
sorry, go ahead.
yeah,
It feels to
yeah.
me,
It's a multi-level system. Yes.
it feels to me that these like dispatch related
Yeah.
arguments like are kind of properties of the subclass, and like if the subclass expects to have those set, um, and won't function correctly without them, I think we should preserve them.
Yeah, so let's talk a little bit about the things here. So what the dispatch keys do is they modify some properties on TensorImpl, which cause a subclass to start dispatching to Python or not. So one reason sort of not to include these in the serialization is in some sense they're part of the sort of functionality implementation of a subclass. So for example, if I have a subclass and at some point in time I'm like, oh, actually I do need to dispatch on sizes strides, and I modify my subclass code so that I'm now setting this policy to true or whatever it is. I guess it's a string. Then if I had been saving it in my serialized format, if I load old versions of the subclass, they would like not actually dispatch in this way, and that would be a very confusing bug to debug because the like missing state would only be visible if you actually knew a particular internal API to interact with. NYC.
Just a quick note that the fact that it is not preserved doesn't mean it's going to do what your subclass implementation is doing. We do not call dunder new or dunder init during deserialization.
So something needs to happen, but I'm just pointing out that
yes.
saving it and then restoring exactly what it was requested is not necessarily what you want. There's also an annoyance here, which is that I can hypothetically have a naughty subclass which has instances that have inconsistent device dispatch settings, despite all being the same class. That seems annoying. Oh wait, let's talk about this underscore new thing. So like, how come we don't call underscore new when we deserialize a tensor subclass? Maybe we should.
Feels like we
Why
should.
not?
There could be some like non-trivial logic.
It's Sam.
I don't remember. I thought it was like I thought pickle doesn't do that or something. But I could be misremembering.
As far as I know, I think pickle calls TP new, but not TP init.
Okay.
Or something like that for custom objects. The main problem with calling dunder new here is that this is going to break weights only. Meaning that no subclass can be serialized with weights only anymore.
Remind the room what weights only means.
Weights only is the safer version of torch save load, such that you cannot have arbitrary code execution happening on loading. The way we do that is we need to control a lot more how are things deserialized and what is allowed when deserializing. The problem with having an arbitrary user subclass done is that this code can be arbitrarily stupid and could be doing eval on its arguments, meaning arbitrary code execution could happen if someone realized such a subclass is in your code base. So we would need to prevent any subclass that has a non-verified dunder new from being allowed, meaning that basically all the subclass, because all the subclass override dunder new, would be disallowed by default, which is a significant regression from what we have today, which is most of them work as long as you don't override things like getAttr or setAttr, which people usually don't.
Okay, I guess that's another point that I want to bring up, which is, so when what do I expect to work when I do subclass serialization today? Like, as in, what is the like feature surface we actually have to maintain with regards to this? Does anyone know?
My expectation here would be that you can have the parameters of your model and thus the content of your state dict be subclasses, and you can save that and you can load that, and that should work.
I can +1 that I'd want that.
No.
And
I'm not talking about what we want to work. I'm talking about what actually works today. So is it something like, as long as I'm not doing a wrapper subclass, serialization works as is today?
pretty much most things do work today. Well, bugs like this, notwithstanding.
So is the
Like you
claim also
can
that wrapper
serialize.
subclasses mostly also work?
The state dict for wrapper subclasses works. I mean, my call, I mean, I just from experience of one, this works. I'm not using any of the non-preserved. I don't think I'm calling any of the non-preserved attributes though, besides their default.
I would be curious if dtensor is using any of these custom things, because I know they do serialize some of these. But
Yeah.
I don't know if Lucas, you know, off the top of your head.
Okay, I want to check some other points in the design space. So we have this thing called tensor flatten and tensor unflatten. Does that help? Is this the underscore new problem?
For weights only, it does not help. No.
You can also execute arbitrary code inside the tensor and flatten.
But my point is that if we're not in a weights only regime, then like most of the inity style, like, you know, call a constructor style serialization mechanisms seem like they work.
Okay, I think if you're not a weights only world, the same way Dynamo or like AOT AutoGAD uses these methods to extract, you know, non-tensor subclass components out of the tensor subclass, we can do that and then serialize whatever you get out of it and reconstruct it from there. Depending on what the user does or like gives us out of the flatten, maybe that will only work for these traceable subclasses though.
I mean, you
True.
can write a tensor flatten whenever. It's the R equivalent of reduce ex or whatever, right? You're always you know, permitted to write your own reducer function, right?
Yes.
Mm-hmm.
Okay, so let me think. All right, let's talk about the security model. So what exactly, Alvin, is the weights only security model for tensor subclasses? Because it still seems, you know, a bit suspicious. For example, let's say I have an exec tensor, which takes in some bytes tensor and then, you know, execs it, right? So, like, nothing's going to stop me from unserializing the tensor and then, boom, arbitrary code execution. So what exactly is our security model here?
So, but that would be arbitrary code execution at runtime of your model, not at deserialization time.
So your threat model is essentially, we must not execute arbitrary code during deserialization, but it doesn't matter to us if, like, just poking the resulting object in the very slightest way causes remote code execution. This just doesn't seem valuable, Alvin. Can you tell me why it's valuable?
It's valuable in the sense that you should assume, like, we have to assume that the local code that you are running, even when you don't initialize things, is okay.
But
you know, your thing is a threat model.
Why shouldn't I assume the constructor is okay too? Like, the constructor doesn't seem like special compared to like all the other implementation code in the subclass.
you can assume it's okay and tell us it's fine. Sure. I think the threat model here is we want something that plugs the obvious gaps we have with our deserialization code while being flexible enough that we can actually make it the default and people are actually going to
this
use
is
it.
this is not like, that's not a threat model, right? A threat model is, this is the kind of adversary that we expect to not be able to, you know, cause a vulnerability, and things outside of the threat model are not considered to be security vulnerabilities.
Okay. So then in that world, the threat model is, given that I have code locally that is not inherently bad, I should be able to torch.load any checkpoint without doing arbitrary code execution. And the threat is someone provides me with an arbitrarily bad checkpoint. My local code is valid, as in it can be doing weird stuff, but it should not be explicitly malicious by itself. But you know, saying you do an exec.
The point I was making earlier was that, but you're disclaiming any responsibility with what happens after I like have unserialized the object.
Correct. And I also claim no responsibility if you allow a subclass that is bad.
Does anyone else have an opinion? This security model doesn't make sense to me, but I mean, I don't know if I can convince Alvin otherwise.
I have opinions,
Okay.
but it seems like, if I'm understanding this correctly, the crux is like your local code might be poorly written, but it's not malicious. And like, to what extent is poorly written, you know, tensor subclass exploitable by this? And it's, I don't know, it's not really clear to me one way or the other how much that is. I don't know, people like, you know, doing eval or exec on like the weights you load seem kind of unlikely to me. But other things might be more likely. Like the Hugging Face model is basically like you control the model definition, but not the like checkpoint, which this sounds pretty much similar to. The part that's worried me about this is just that the loading is very complex with this complex state machine that makes it hard to be confident that that doesn't have exploits.
I am in discussion with Central Security here at Meta to see if they can actually build that in a secure way from their point of view. Would that make you happy? Does that satisfy you, Ed, or are you still not happy with the state of things?
Well, I mean, I'm willing to defer to Sam.
Well, you shouldn't. I wouldn't defer to me. I don't.
Did we have another hand? Was there one in NYC?
Well, I had a hand up for a second.
Oh yeah, sorry, Greg.
Like, what is? I guess I'm missing what's different about tensor subclasses from like any arbitrary object with respect to the threat model.
Well, we control like base tensor and can verify it a lot more than arbitrary subclasses, right? I feel like that's the big difference, is they might override one.
But I could put some arbitrary object like on my I actually don't know what happens if I serialize it on a tensor, but like on a module I can.
Oh, well, but weights only says we only attempt to unpickle things that are well-known objects like tensor.
I see. So we get in this situation because the weight is a tensor subclass?
Correct. And I think the way we work around that question, Greg, for all the other subclasses, we basically forbid them, and the user has to explicitly say this is safe or not safe. And you could argue this is not much better because it's going to be hard for the users to actually know what is safe and unsafe for especially poorly written classes. The point we're making here specifically for subclasses is because we have a lot more control over them, we can guarantee safety under these constraints of these kind of subclasses a lot more easily. And so that makes, these things that are going to be weights, we can actually allow. I think, Ed, if you want to dive more.
I missed something. You're saying that we have an allow list for certain tensor subclasses that we control that can pass through weights only?
So we have an allow list that anyone can add anything there if they verify the code and the code is safe. The subclass discussion here is by default, subclasses that have specific properties will always be allowed because we can verify that under these properties, they cannot in any way do arbitrary code execution during the deserialization. I think if we want to continue discussing that, I'm happy to do it here, but I think it would be good to do it with Michaela involved. And she has a longer doc that explains what we consider to be safe, not safe, and all of that. That might be a good read as well.
Okay, let's pop the stack then. Okay, so going back to the beginning, Joel and Brian, the motivating use case here was someone wanted to use their stuff over data loading. Is that right?
That's right. Yeah.
So data loading is not the weights only case. So I guess in some sense we can sort of kick the can on weights only by being like, forbid it, and then figure out how to poke holes in it in a way that's safe. Like that's always like a safe stance to take. Unless it's BC breaking, then you're sad. Sorry, NYC.
The point with calling done on you is you need the arguments for done on you.
Well, I mean, but that's what like tensor flatten is for example.
But that means we'll need to ask the subclass implementer to give us these arguments for their particular subclass.
Yes.
So it'll require tensor flatten and unflatten to be implemented.
Yeah.
Which is
or another magic method we want you to decide that tells us how you build a tensor.
Yeah.
Okay, so I just want to understand if we know how to unblock the person here in question. So in order of like most specific to least specific, the most specific way they can unblock is by writing their own reduce function on their subclass. And then they're done, right? That's it. Like nothing else needs to be done. Is it easy to write a correct reduce function or is this difficult?
It's pretty easy. We do it with NGT. It's just if you want the extra logic for getting the like attributes out of the state, whatever, all that stuff, you have to know about some helper functions, but it's not too bad.
It's also a function you can nest relatively easily. So you can call super reduce x and then wrap that into your custom handler if you just want to tweak the behavior.
Okay.
Also, to be like very precise, the person who pinged Brian was just blocked by D-type, and that fixes in, so they're not blocked anymore.
Okay. So then, more broadly, do we have an attitude on how important the default serialization story is for tensor subclasses? Like, does anyone want to make a claim? This is important. Like, we absolutely need to solve this. Or does anyone want to say, whatever?
If we audit all the usages of these dispatch args within the subclasses we're working on now and ensure that there's a custom reduce function for those, then I think
No. I'm not saying how we should do it. I'm saying, does anyone feel strongly about like having a default where you write an arbitrary tensor subclass and it just works when you send it over data loading to try to save to disk?
I would
I don't
say yes, it should.
I guess one argument is pre-dispatched export. If your model has subclass weights and you export pre-dispatch, then you should expect to see like the subclasses when you export.
Okay, but remember, you can always like write the reduce function yourself. Okay, so what we're specifically evaluating is it important that by default, without user intervention, these subclasses have to be serializable? Alvin, do you still have the same opinion?
I would say, from some of the feedback we got from quantization subclass, D-type subclass, I think the feedback has generally been there is already too many knobs for them to tweak and too many things for them to know. So if we do have a simple mental model of what the standard should be, I would say yes, I think it should work out of the box. And I think we can come up with a simple enough mental model of like what should happen when you serialize a tensor. What do you get out of it, on the other hand?
So then you have a proposal for the default behavior. Is your proposal to serialize the dispatch info, or is it something else?
In this case, I would expect yes, to preserve everything as is. Either preserve everything as is or raise an error if we say we don't want to do something, which is what we do for autograd, for example. Any tensor that has a grad FN or that has a history for autograd, we just do not serialize it. We'll raise an error saying we don't want to be in the business of serializing autograd metadata. You cannot do that. So
but
if
I
there
also
are some of
strongly
these,
feel we should not be in the business of serializing dispatch keys. Like, I do not actually think that is reasonable, like default BC
Okay.
surface to expose in a serialization format.
okay.
yeah,
I think what I had in mind are the dispatch size, dispatch device,
No,
dispatch
I
layout.
also
These
don't
sounds
think those booleans should be in the serialization format either.
why
In
is that?
some sense, I would like to make a BC breaking change where these things are specified on the class, and so you don't have to pass it as explicit arguments to make wrapper subclass. Instead, we always read the values off of the class object to determine it.
You mean dynamically or class construction?
I mean, there's a few ways you can do it, but like one simple patch, which wouldn't take long to write, is instead of having make wrapper subclass take these as arguments, there are just some special attributes on the class that it reads them off of. And you have access to the class because you're passing class to make wrapper subclass.
That seems reasonable to me. It fits my mental.
Yeah. I'm happy if you want to say this mental model would be all the arguments to make wrapper subclass are serialized and preserved through serialization. Anything that is read through the subclass is obviously updated as the subclass is updated.
Yeah, the point is that like you don't need to serialize this because it should be the same for every instance of the class. It's a property of the class, not the instance of the object.
Yeah.
We probably can do this change. Like, it's a little BC bricking, but like these are very difficult to use APIs anyway. I don't think we have too many call sites.
And it seems really strange if on a per instance basis this changes for a given class.
Yeah. Well, I guess if you want to pop the stack one level more, it's what we discussed a long time ago. The user should not have to write their own dungeon new, so that they wouldn't have to call these objects directly. But that's another kind of worms.
You're kind of there is like you can wrap it up, but at the end of the day, you're putting something in dungeon new. There's no way around it. Okay, I'm kiboshing this topic for now. Thank you for all the discussion. Let's move on to some of the other topics. Okay, so second most upvoted was updated plan for unspecialized float input output. So that's me. So let me go ahead and share my screen. I want to share what I want to share. I'll share my entire screen. Okay, so this is the patch that I wrote. Sorry, live streamers. Let me fix the live stream. Okay. I've evolved the plan a bit. So some of you may remember a few weeks ago I was like, we should have a guard FX graph to capture, arbitrary floating point computation for graphs. But then I figured out I can just put it in the shape-n graph. So here's the plan. So the plan is that, okay, so let's first look at the test code that is particularly useful here. So here I have a simple program. So what does it do? So it takes in a float as an argument, and it also returns a float as an output. And in this particular example, I don't actually use the float for some compute, but you could imagine this is x plus y. So I'm adding a tensor and a float together. And so what do I want this to compile into? So naively, I would just have a float argument and a float output. But this will break all of our backends, which cannot deal with this. So we're going to do something different. So what we're going to do is when you have a floating point input, we're going to treat it as a tensor, as a 0D CPU scalar tensor. And if you have any float outputs, we're also going to treat them as 0D floating point tensors. And the way that I'm going to implement this transformation is in 2 steps. Step 1 is purely changing the input-output signature for the graphs that Dynamo produces. So what you can see is that, yes, I take in y as a tensor, but then what I do is immediately I go ahead and call .item on it to give me a float, like a sim float. And when I get a sim float out as the output, in this case the multiply, I will just wrap it up into a tensor using scalar tensor and return that. So all of the internal computation is still done using regular floating point operations, but I've just changed the input and output API in Dynamo to have a friendly UX. And my plan for what to do with this is I'm going to run AOT autograd on it. So AOT autograd will understand how to do tracing through sim floats. It's fine. We know how to trace through simints. It's the same thing. And then I will have a pass, which will try to push these .item calls as far down as possible, hopefully canceling them out with operations with tensors or a torch.scalar tensor call at the very end of the graph. So in the steady state, you only have tensor inputs. Any questions so far? Yes, Brian.
I guess another way I can imagine doing it is just you have Dynamo rewrite the compute to be tensors instead. So what's the high level motivation for doing that?
Yes, I have flip-flopped on this a lot, and I may flip-flop on it again when I actually try to implement it. The reason why I currently think the conversion from float operations to tensor operations should happen as an FX pass is primarily because this needs to be done on a per operator basis, right? Like if I add a tensor and a float together, there's something about addition that I need to know to like work out the type promotion and all that stuff to convert it into a tensor operation. So I do this after AOT autograd. That's at the point in time when I've normalized everything into A10 operators, and now I can like just do the normalized transformation. Whereas if I do it in Dynamo, then I have to deal with the much expanded set of allowed functions, which can have all sorts of not normalized things, and especially like prior to us inlining through NN modules, because I know Animesh is working on turning on inline through NN modules by default. I would even have to like deal with arbitrary NN modules, for example, if they happen to take in float inputs. If I did it in Dynamo. There's another reason is like, if I do it in Dynamo, it's sort of like being done on the fly during tensor variables, and that seems like a little more difficult to debug. I don't know. Like that was the other thing that I was thinking about. Yes, Jiangshu.
Like I have like a dumb question, which is, if we want to do it at Dynamo layer, does it affect like torch export in the sense that it will diverge the behavior of like strict and non-strict export?
This is a great question for export. So for one, export doesn't even support integer inputs to graph unless this has changed. Like a few months ago, I checked and you did not support inputs. So I'm sure you don't support float inputs either. So like, it's kind of like, this is like a non-question because export is just not there yet. But let's say that export did support float inputs. And this is kind of a interesting problem, right? And the problem here is, how does export deal with calling convention changes? That like, I'm pretty sure export does want it to be float tensor inputs in the final exported product. Like that seems like better for everything else that has to deal with it downstream. So you'll have to like somehow negotiate like, oh yeah, this thing in the user model took a float, but it has turned into a tensor, and that's what you have to send the exported thing. And like, I need to tell the user somehow. I don't know what the right way to do that is, but like, that's a problem that export has to solve if they want to get into this space. And of course, you can always like fix it by just, well, okay, it's not so simple, but like, maybe we should figure out how to do this. You could fix it by just simply forcing the user to rewrite their interface so that they pass in the floating point number as a tensor, and then they call item on it and then do stuff on it at the end. This is almost as good. The one thing it's not as good is that if you call item on a tensor today, you get an unbacked float. But something very, very interesting happens in this example. So we got to look at the other test, which is I support guards. So although this turns into y is a tensor, and then I call y.item, and then I use the result of item for the rest of this, I can still do conditionals on the floating point value. And this is done via some very inside baseball dynamo hackery, which is that when I manually do the item call, and instead of creating an unbacked float, which is what normally would happen in an item call, I'm actually like, I know what the value is because, I'm in the process of wrapping the real runtime value. And so I just instead directly create a backed float with the real value and the source. And by a hilarious sequence of events, which the reason why it took me so long to write this PR was I was like reading code and trying to understand if it would actually work or not. And the answer is it does happen to work by like a hilarious sequence of like things people have already put into Dynamo and like just sort of setting everything up all correctly, and then it all kind of just works somehow. I was very amazed when it just kind of worked out. Okay, any more questions?
Does this are there any difficulties of like converting FP64 to FP32 and did you run it?
Wonderful question. So I am always doing Oh no! Okay, this should be F64 actually. So this is a bug. I plan to represent floats as F64 scalar tensors, and I plan on correctly implementing the promotion rules so that if I add an F64 scalar with an F32 scalar, I end up with an F32 scalar, not an F64, which is what would normally happen. Sorry, when I say F64 scalar, I meant float, like Python float. And yeah, and then you guys can do some optimization past that reduces the precision if that's something you want to do. That's sort of not my problem. NYC?
I'm curious, what is the major difference between having a backed versus unbacked cement, and what makes the magic
It's
happen
this.
here?
This is the big difference. So if I
So
rewrote
if
this
there is,
program so y was a tensor and then I did y.item equals 5.0, it would fail to trace with a guard on data dependent error.
and if there is no guard where it's
If there's no guard, like in this example, it would trace, and there isn't really a difference.
okay. Thank you.
Sherlock?
I wonder how do you handle integer, like how in the graph inputs? Like,
Oh,
is this, are you
integers
planning
is
to
different. Integers stay integers, and there's a long and sordid story about this. But essentially, the reason why I believe this is right is because unlike floats, integers are often used for size computation, and so it would be really dumb if like I pass in like I had an integer which was like, you know, size of a tensor, and I wrapped it into a tensor, and then I unwrapped it, and then I sent it to like a factory function. Like this is like not good. So we're supporting integer inputs to the FX graphs, and export needs to, like, you know, support integer inputs. Like I think this is going to be a permanent feature. If expert wants to say no, this is really terrible, we can talk about it. But like, you know, there was like a difference. We were like, ints, it's worth it. Floats, it's not worth it.
I think export would prefer to have tensor only graph inputs. And at the moment, we currently didn't implement anything for integer typed graph inputs. So when I look at like floats, I think this, yeah, it matches what we want, you know, converting this into a float. But yeah, and this is only internal, like behavior is only like this for strict
Okay.
mode export.
It is true that what I have done here, I could do for integers. And the difference is that although for floats, I would expect to be able to delete the items entirely, for integers, eventually, you know, you feed it into a factory function, and that would have to be an item call and then, you know, do it. So, okay, maybe we should talk. Maybe I do need to do a version of this for integers. I don't know. I still think it's silly to send in sizes as tensors, but, you know, yeah, this is something we could talk about. Brian?
Question related to Albin's question, actually, for like, or do you think it would be reasonable to give the same treatment to item calls from scalar tensors that users pass in to the sort of special that
Yeah, I think this is a good idea. We probably should do it. It's just so ugly. Like, the way I've done it is like kind of horrifying, which is like I first have to like create a what do I even do? I have to create a tensor graph input with an unspecialized Python variable, and then I need to manually, man. And then I have to manually create the like item call and like manually allocate the symbol. I mean, I can put this in functions and stuff. I probably will, but like, yeah.
Or can't, like, when we get a graph input that we have to turn into a fake tensor and we see that the graph input is a 0-dimensional tensor, can't we just like put the constant into the fake tensor? And then if you later that item it, then we don't need to do anything special. We just like have the hint.
So the answer is no, because, well, I mean, morally, yes, but implementation wise, it is more complicated, and that's because of this thing. So there's this extra flag that people added to GraphArg way back in the day, which is called pass arg as tensor. And this basically is what lets you. Actually, is this even relevant? Okay, maybe not. Maybe it just works. So you're saying we know what the real value is on the fake tensor, and then when we call item on it, we make a backsim it, so long as the fake tensor has a source, which it probably does. Yeah, okay.
If it's easy, I don't know. I could believe it's reasons why it's
there's
painful.
like silly like variants that are harder to support. Like for example, if I call .toList on an input tensor, this would not work, but for silly reasons. The silly reason it doesn't work is toList turns into do a view on the input tensor and then call item on the view. And the view is no longer an input, so you now need like source tracking on tensors so that eventually you can get out the actual value in question. We actually kind of want to do this for other reasons though, so NYC.
Yeah, if I understand Brian's question correctly, it's like, can we do the same thing as in like build a not on backcement if we know the initial value that the user passed in along? But is that true? Is that the question? I might not be understanding.
Yeah.
Okay, so if so, then is it the same as if we if you just did like torch.zeros or you started a scalar tensor and you know its value at creation time, you could also do the same thing, right?
Well, for torch.zeros, what's more common? Is this true? You could also, but we actually just do constant propagation, so we just end up with 0 if you call .item on it.
Oh, well, I was asking because this is how I'm imagining it. There's a lot of code in Optimizer that does like Python float math with step, which is a scalar tensor that starts at 0 basically every time where it's loaded as a scalar tensor. So it's like very I feel like now they could just work. We have a lot of code today that specializes on step.item, and it's like, can this PR just remove all that specialization? Perhaps.
Yeah, we should try it.
Yeah, that'd be cool.
We should try it.
Okay.
Okay, thanks for the lively question session. All right, so let's go ahead and do some quick stuff. Okay, David, are you still here? We're just doing some rapid updates. Okay, tell us a little bit about the NJT inference stuff.
Yeah. So I guess actually what I was so I guess for inference, I think we're kind of aligned. Like it seems like the plan is just we expect if you want to run NJT in inference, like first you can't be using torch script, and then like we're going to trace through like the subclass stuff before we actually try to run anything in C++. So I think for that we're okay. I guess the other thing that like recently was kind of annoying is just like there's kind of a lot of overhead in subclasses for Eager. And I guess like we're looking at some benchmarks for like some SDPA stuff, and we're finding like things were just like kind of too slow. I can share.
Do you have folks who are helping you on this, or is this just, hey, this is slow, and so we're not going to do it?
Yeah, I mean, I think right now it's sort of like it's slow, and I'm not really working on it actively, but I don't know if people have ideas on it. I can show the traces if my screen sharing is working. Okay, it's my screen. I can't screen share right now, but basically like when we do like an SDPA kernel, like we like for reasons I'm not completely sure, but I guess like we want to like transpose like the inputs before we run the SDPA kernel, and so we end up having like 6 kernels that like 6 view kernels that we need to run before like SDPA, and when we're running with like subclasses, these views take like a lot longer on CPU. I haven't really looked at why, but I assume because we have like this dispatch logic that goes through Python. And so we end up with at the end of the day, we end up with like just a lot of CPU overhead that's making and the NJT like SDPA is like way slower than if you implement it in Triton and like not use nested tensor. So I think it's like not a problem if people are using PT2, but like if you're sorry, if people are using PT2, but like if you're using eager, I think it is kind of it may prevent people from using like at least NJT in cases where like they care about eager performance. Yeah, so that's kind of all I had.
Okay, thanks. Any comments? Okay, Lucas, you want to tell us about async checkpointing? And we lost Lucas. Okay, let me show off the data-dependent puzzlers. Because someone wanted to see that. So I have some data-dependent puzzlers. So the idea behind these puzzlers is that it's pretty common when you're working with data-dependent shapes to end up with errors. So like here's an example error. There's a little program. I called toList to get out some unbacked cements, and then I did a conditional on them. And this doesn't work because it says, hey, I couldn't guard on this data-dependent expression. I don't know if it's true or false. Help. And in this particular case, you can fix it by just adding a torch check that says, hey, these two things are equal. So that, yes, we know that in fact they're equal. And if you run it, oh no. Okay. And then we run it, now it works. And so the notebook is just a lot of these exercises doing all sorts of different situations. I basically went through the entire history of all of the bug reports we've done for unbacked cements to distill out a bunch of interesting ones to share here. And yeah, that's all. Okay, so that's what I want to say about that. Okay.
Wait, Ed,
yes.
Question. So I know the title says no solutions, but I think there were links in the thing that were like, read this first. Are those like, if you read it, you should definitely be able to solve the puzzles? Or are there like other resources that we should be looking at?
I think the linked docs is supposed to be enough, but it's possible that it's not, and I'm just overestimating like how much inferences people can do. So like any feedback like that, I am definitely interested. I already got some feedback where I have a hint on one of the puzzles being like, you're going to try doing torch.check and it will not work. And the feedback was basically, oh, actually I did torch.check and it worked. And I was like, wow, I was not expecting that. Okay, 2 minutes left. Let me see. James, give us a little update on AOT Autograd caching.
Can you hear me now?
Yes.
All right, great. Yeah, we're making some progress here. One of the things that we've been running into, I think that is been challenging is just the way that AOT Autograd kind of structures the wrappers that it calls when it executes its compiler. And essentially, one interesting issue here is that a lot of the wrappers that, a lot of the transformations that AOT Autograd does, it does in the form of these closures where the closures take in the flat arguments and the flat function that gets passed in to be compiled. It does some transformation on those flat tensors, and then it compiles it, and then it creates a runtime wrapper around that, all in the same function. So like synthetic bases are an example of this. Functionalized RNGs wrappers are like this. And because they're all in one big closure, if you try to cache it, essentially need to be able to cache the runtime wrapping part, but not the like compile time wrapping part, because you've already done the compile when you hit a cache hit, right? So right now what we're working on is just refactoring some of this code so that instead of being a bunch of wrappers that are actually, to be fair, also just really hard to understand because they're written in like composed wrappers like this, just converting those into a pre-compile step and a post-compile step, and then running the pre-compile step, then running the compiler, and then running the post-compile step. So converting something from it being a bunch of like nested closures into a more iterative step. So I've been working on that. Once we do that, then the nice property about this is once you understand how each of the phases and each of the transformations saves information to be used in the runtime, you also exactly get the set of things that you might need to cache in order to like regenerate the thing when you're generating cache. So that's what we've been working on, and we're making decent progress on that. So
thanks for the update. Any questions?
Yeah.
I have one silly question. How do you like the file organization for AT Autograd? Do you want to move that around too while you're refactoring?
I barely understand it, so it's a little hard for me to
I also
say.
do not understand it. So
it's not only the file. I think it's more just like the interlock dependencies on it make it pretty hard to refactor in general. And I like sometimes there are these wrappers that are like supposed to wrap around a function and they get called on a partial, a functools partial. So the application of the wrappers are themselves wrappers, and then it goes like backwards. It like reverses the order twice because it like reverses it once because you're doing a stack, and then it reverses it again because you used a partial on the stack. So like it's impossible to understand what the code is currently doing, which means that by refactoring this way, I think we're also going to get a lot of code clarity, not only for caching, but also just like in general, you're going to see like, oh, we're just going to run a bunch of steps one at a time, and then we're going to compile it, and then we're going to run a bunch of steps afterward, and that's it. You know, that's the hope of this. We'll see.
Okay, thank you. And we are now out of time. Okay, thanks everyone. See you all next week.